Okay, so we can start. Do you have any questions before we start?
Yeah, I've got a couple about the project.
All right. Yeah, so fire away. Should I pull it up? Yeah, let me pull it up.
Yeah.
Okay, again, the project is online on Canvas, and it's due in almost exactly 2 weeks. So, yeah.
Okay. Question 1, part C, when you're calculating the error.
All right, so question 1 is basically the heat equation with an extra term. You're given initial conditions, boundary conditions, and you're given everything you need to discretize the equation, and you have to solve this in time. So if you go to part C, all right, this is part C, and you're told that if you go to steady state, there is an exact solution for the temperature in the room, okay, and that follows this equation. And your numerical solution will, of course, have some error. And this is the one way to compute the error. All right?
In equation 5, where you're doing that calculation, is n like the total number of like nodes across the bar at
yeah, so
whatever?
you're basically computing error at each node, and you're summing it up all over the rod. So every grid point that you add.
So you're getting a total error for each time step.
Exactly.
Okay, so for the next part where you're calculating at different segments, so should we compare the plots of the error for each time step to each segment, or should we do something like...
Okay. So the question is, for this problem, you have to do a space convergence and a time convergence. You basically have to see how fast the error drops as you use smaller grid cells or you take smaller time steps. And so these are just some suggestions. You can break up your rod into 10 segments, 50, 100. But the question here is, what time step do we compute the error at? Right? So if you go back here, you're given it's t exact at steady state. And you've been told to run your simulation for 50 seconds. That should be roughly enough to get you to steady state. After that, the temperature should not change. So just take your final solution at the very last step, and then compare the difference with this exact equation. Does that answer the question?
Yeah, so I'll look at the total error in the rod at the last time step.
At the last time step, yes.
Okay.
Right, okay. And then for one of the parts, where is delta t? Yeah, so here you have to do the same, but in time. You fix the number of points you use for discretization, and then you keep changing your delta t and see how the error drops. Again, do it for the very last time. Okay, all right. Anything else? Okay, so before we start today, I want to show you some of your videos from the homework, all right? So again, I will not say who this belongs to, but it's just to give you an idea of what people have tried and what are the different ways you can visualize data. So this is one submission for the grid, visualizing how the grid changes in time. Okay, and they have actually colored the grid, well, the flow field with vorticity. Okay, and then there's another submission which uses a different color map, and there's a different background color. So you can do many, many different things. And again, this is a very subjective thing. So you keep playing around with visualization until you get what you want. Okay. Then for looking at the flow field, so the question was, what is the best way to visualize the flow field? So, you know, somebody who's watching the video knows what's happening. All right, so let's look at a few tries. So here they have visualized vorticity again, and that's a certain color map, all right? And then there were some submissions that also visualized the flow field in the whole domain using velocity vectors. And this, again, you can compute in the same way as we were doing when I was showing you ParaView a few lectures ago. Okay, and yeah, the background here is colored with vorticity. Black is negative, red is positive. Okay, then there was another nice submission which does the same thing, but now you can even color. Let me pause this. You can even color the velocity vectors themselves. And in this case, the vectors have been colored with channel 2, which was V velocity. So you can do many, many different things. Okay, then there was one more submission where we see vorticity, and there's also these white lines, and these are basically contours of vorticity. So you can see it's another nice way of visualizing what's happening in the flow field. So there's no right way or wrong way. It's just you have to try to be as informative when you make these visualizations. And if they look nice, that's, you know, a bonus. When we, towards the end of the class, if you let me, I will select a few of your videos to sort of display at CTEC. We're thinking about having a monitor where we display nice videos. But yeah, that will come later. Okay, so, all right. Any other questions? No. All right. So let's switch to this for a second. All right. So last class we were deriving the stability of the advection equation, and I've just this nothing new here. And we were missing a minus sign in the end, and I figured out this is where this should have been a minus instead of a plus. So just fix this in your notes and then follow through. So all at the correct places. You have sign changes. Okay, and eventually you will get that it's alpha minus 1, which is what we said the correct answer should be. Okay. So again, the minus mistake was here, towards the very beginning. Okay. When we were talking about advection, there was this concept that we mentioned, upwinding. If you remember, upwinding is basically biasing your derivative towards the direction where information is coming from. And what we said was, okay, I'll leave this up for just a few more seconds so you can fix it. It'll also be on the video, so if you like, you can go back to it. Okay, so for upwinding, we said, okay, this was our advection equation. Del phi by del E plus U del phi by del equals 0. And for upwinding, we said we will say this is I n plus 1 minus phi I n over delta t plus U I n. And if U I n is greater than 0, what happens here? Do you remember? Delta x, yes. What approximation should we use for the first derivative in space?
Upward.
Upwind, yeah. So let's say it will be phi at n. I what?
I.
J or I.
Yeah. I and
I and I minus 1.
and I minus 1. Yeah, exactly. So we're saying the velocity is positive, so we have to go left, right? So that's current minus left divided by delta x gives us the derivative. Is this the only possibility? So this is the first order discretization. First order discretization for del phi by del x. Am I limited to using this?
No, you could go the other way.
You mean I can go to I plus 1 minus I?
Yep.
I should do that only if this is negative, right? Because we are restricted to, we have to upwind, right? We have to use upwinding. So as you were saying, yeah, we could go I plus 1 minus I, but only in the case that this is negative. Okay. So is there are there other higher order derivatives for del phi by del x that you know of for the first derivative? Center difference, yeah, that's the second order that we can use here. But that's the very first thing we saw. We used the center differencing, it was unstable, always. Okay. So we cannot use that second order center difference. So what about the third order? We can try a third order approximation for the derivative. Okay. So how do we figure out what a third order approximation looks like? We go to the source of all knowledge and say finite difference coefficients. All right. Okay, this is something we had seen when we were talking about finite differences. So this, if you take the first derivative, order 2, you'd go one left, one right, and divide by 2 delta x. That's basically what this is saying. All of these are even order center differences. Okay. If we scroll down a little, this is the odd order one-sided differences. Okay. Here, so you see this first order derivative is just go left, stay at current cell, and divide by delta x. So that's exactly what we wrote, right? It's phi j minus 1 over delta x. If we want to use a second order accurate one-sided derivative, that's one possibility. But we prefer to use upwinding. So what you can do then is, where is my minus 3 plus 4 over 2, yeah, okay, all right. Yeah, actually, yeah, let's use that one-sided formula. So this is one-sided, right? You see, one side has more bias than the other. If this is my current cell, you go 2 right. This is my current cell, you go 1 right. Okay. So minus 3 over 2, 2, and minus 1 half. So we will use this one. And you can write that as a derivative as, so let's say, so let me just write down the coefficients. Coefficients are for 0, 1, 2. We have here in the table 3 over 2, 2, and minus 1 over 2. Okay. So del phi by del x can be written as minus 3 phi I plus phi I plus 1 plus phi I plus 2 phi I. Oh, no. written as over 2 delta x minus 3 pi I plus 4 pi I plus 1 minus pi I plus 2. Make sense? So yeah, I basically took the coefficients from the table, and this just, can be written as 0 at 1 is my current, and the coefficient is minus 3 over 2, minus 3 over 2. Plus 1 goes to a plus 1, coefficient is 2, which is 4 over 2, and plus 1 becomes minus 1 over 2, it's minus 1 over 2. So yeah, instead of using this first order approximation, we could have used this one. Okay. And that's perfectly fine. And this is one of the commonly used discretizations for equation. Okay, so we could also use phi n plus 1 and phi n. U I n. Okay, so
I think that's a derivative at I plus 1 if you do an Euler expansion.
This?
Yes.
Why do you say that?
So the second term will have 4 delta x d phi by dx, and the other term will have 2 delta x d phi by dx. So it won't get cancelled. If it has to get cancelled, it should be a derivative of phi I plus 1.
You said the second term will have. Did I miss something out? Wait, let's go back to the table. Okay, let's go back to the center derivative and let's make sure what we're doing doesn't make sense. So for the second order, what we do is I plus 1 minus I minus 1, right?
Yeah.
And that's what these ones are,
Mm-hmm.
divided by 2 delta x. 0 is my I,
Okay.
okay? So using that same logic here, 0 is my I. If you want a first order derivative, you would do I plus 1 minus I, divided by 1 delta x, all right?
Yeah.
And that's how we're using this formula, right?
Mm-hmm.
Okay, so let me switch back to the document camera and let's make sure. All right, so we have 0, 1, 2, minus 0, 2, 2, minus 1 over 2. So this goes to I, this goes to I plus 1, this goes to I plus 2. Does that make sense?
Yeah. Yeah, the table did, but
This does not?
I'm taking the Euler expansion of the terms inside, and I'm trying to make sense out of it. That's where I'm getting stuck.
You're doing the Taylor series expansion of I plus 1?
I'm trying to get it.
I cannot do that in my head. I will have to do this
Okay.
out on paper, but unless the table has some mistake, this should be okay.
Yeah.
Okay. All right. So instead of using this first order term, we could have used. Again, here we are biasing to the right. So what should u be? This is less than 0 or greater than 0. Yes.
It's upwind, right? So
Yeah.
It has to be positive.
It has to be positive. If u is positive, which direction would you bias in? Left or right?
Information comes from left to right.
Yeah, so-
biasing means.
All right. Okay. So this is important. Okay. So if we have these grid cells where we have u that looks like this, right? Which way would you draw your biasing box?
To the left.
To the left, right? And here ui is greater than 0.
Okay.
Okay, makes sense? Now we're biasing to the right, so that means once more.
It should be less than 0.
Yeah, this u should be less than 0 for this formula. If you have a grid cell where it's greater than 0, you flip these. It's symmetric. So, all right, for this particular case, we will have minus 3 phi I plus 4 phi I plus 1 minus phi I plus 2. Yeah, this makes sense because u is less than 0, which means the information is moving from the left, which means I will bias towards. Information is moving from the right to the left, which means I should bias towards the right side. So yeah, that's basically that's the basics of all of this. Once you're comfortable with this, you can do any high order discretization yourself. And for the projects, we will use these simple things. Okay? For your own research work, you can do high order things. Okay, so that's what I wanted to tell you about what remained from the last time. Any questions about this? All right. So now I want to show you something very different from all these Eulerian schemes we have been talking about. Okay? It's a very elegant solution to this advection problem. And again, our governing equation is always del phi by del t plus u del phi by del x equals 0. And you might remember this is just the material derivative. Can one of you remind us what this material derivative represents?
Continuity,
It represents continuity if you talk about this, right? Del rho by del t equals 0. This just by definition it means incompressibility. But now my phi is any passive scalar. It can be temperature, it can be ink concentration, anything. So physically, what does this represent, the material derivative?
The derivative if we are in the reference frame of the particle.
Yeah, it means that if we are following a blob of fluid, a packet of fluid, and we follow it along, we jump on the fluid blob and then see how things change in time. Things here, if phi is temperature, how the temperature of the blob changes in time. Then this material derivative applies. Okay. If we jump back to the lab frame, so this is what we had drawn almost the very first class. There was a channel, and there was a blob of fluid that was going along, and there were some candles over here heating the water, and the temperature of the blob would change in time, maybe because it was radiating. Okay, it contained some weakly radioactive element, and in space it would the temperature would change because it's being affected by the fluid field, the fluid flow U. Okay, so basically that's what it means. All right, so if that's what it means, why don't we do our discretization like that? We mark every blob as this can be blob 1, all right? So let me say we have blob 1, we have blob 2, and we have blob 3. Okay? And we can basically measure what the temperature of each of these blobs is, or the phi of each of these blobs is. And then we can follow it in time. Have you seen this concept before? It's called a fully Lagrangian solver. It's a very straightforward jump from here to here, right? Mathematically, we know this represents the Lagrangian derivative. And conceptually, it just means we see how things on 1, 2, and 3 change in time, and we keep following. What's the challenges that you can think of in doing this? And this blob, we have to have sufficient number of blobs to discretize our whole fluid domain. Right? I'm just using 3 for an example. What are some of the challenges?
The reference point will keep moving.
Yeah, these blobs keep moving in time. And we have no static reference to know where they are. right? So if we had used, let's say, a grid to discretize this domain, our grid points, which are the computation points, do not change in time. They stay static. This is a static grid. And here, the blobs keep moving in time. My computational points, which are the blobs themselves, they keep going all over the place. So that's the first problem. You have to keep track of each individual blob. And computationally, conceptually it seems easy, but computationally this is very, very different. You have to assign an index to each single blob. So this, again, is blob 1, blob 2, blob 3, blob index. This is blob index. And then you have to figure out what XY position of blob 1 is, what XY position of blob 2 is. Here, you don't have to do any of that. You always know that what Y and X positions of each grid. So that's one point, bookkeeping. So this is heavy bookkeeping. There's a second big disadvantage. In PDEs, we always deal with derivatives. Okay, so how is that a disadvantage in this case? Or if you think of it, how is that an advantage in this case? Do you know how to compute derivatives on something like this?
So I think the discretization will be different for each one. Is that the point?
Yeah, so here there's no regular discretization. Here we have a very nice square-like grid. Here, it can be whatever, right? It depends on how your fluid flows, how much time you track in. So with a nice discretization, you know how to represent derivatives. Okay. That's one of the biggest problems here. Computing derivatives is not easy when you have an unstructured grid. So, what was I saying? That's the second disadvantage, which is computing derivatives is difficult. But still, so these are disadvantages. This seems like a very natural way to do it. So how can you think of a way where we can perhaps combine these two approaches to come up with an intermediate solution?
Averaging.
Averaging how?
For example, the minimum discretization required for any of them, consider that for all of them.
The minimum discretization
Delta
required.
X, for example.
Okay, so delta X so are you talking about the blobs or this?
Blobs.
All right, so, but delta X, okay, so you're saying if the delta X between these two blobs is, let's say, 0.2 meters and these two blobs is 0.1 meters, everything has a 0.1 meters, okay? Yeah, so that's sort of the direction we need to go in, okay? We need to use a combination of this Lagrangian and Eulerian approach. And this is called a semi-Lagrangian delta X. It's semi-Lagrangian in the sense that you do this sort of tracking of a blob, but you also have a static grid at the same time. And if we consider what it looks like in practice, we can take a look at a few animations. All right, let me switch to my Okay, so again, we have this grid that I just drew on the on my sheet, and for this case, I've shown my grid nodes to be centered at the cells. You could also do this where the grid nodes are at the intersection points. Right? It's just a different representation. We will eventually see what happens when you do that, but for now, it's fine. So, what should I do now? You tell me. What would the first thing that you do be to do this advection? So here, ignore the diffusion. This is the advection term, diffusion term. Let's assume this is 0 for the time. So I give you, let's say, ink concentration on this grid. Here the ink concentration is high, and slowly it becomes 0 as we move away. And you're told to do semi-Lagrangian advection. What is the first thing you would do? Any ideas? Right or wrong, we don't care. What is the first thing you would try?
Probably the Eulerian.
Do it the Eulerian way?
Yeah.
Okay, so you want to discretize this in time and in space using an upwinding, just as we were talking about right now. All right, yeah, but that would be a fully Eulerian scheme. We haven't incorporated this concept of moving blobs, right?
You can do some interpolation.
All right, yeah. We're going towards where we need to go, so we will need to do some interpolation, but interpolation of what?
The scalar field and like how we know the position of the grid points.
Okay, we know the xy locations of the grid points, each individual grid point. Okay, then?
And then we can say like after this time where its position would be.
Yeah, so that's exactly the concept of the semi-Lagrangian approach. You start with the grid, and then you say each grid point is a fluid blob. And the velocity u is known at each grid point. Okay? So what we can do is with that velocity we can move. That's exactly this direction you were going in. Once we move, we know our new location. All right, what next?
You could redefine the grid
Yeah.
for that new
So-
location.
Yeah. So you said you can redefine the grid. You're not guaranteed that u is the same at all grid nodes. So this u can be 2 meters per second. This u would be 1 meter per second, but in the opposite direction. So if you recreate your grid after moving all the grid points, what happens to the grid?
You have to interpolate.
Yeah, exactly.
The data.
Yeah, that's exactly the concept. So if you, let's say this grid moves to the left, this grid point moves to the right, and after that, if you just, let's say you say that this is my grid point at the next time step, this is my grid point at the next time step, and if you form a grid, it will be a very irregular mesh. You will not have this nice square-like structures anymore. So what we do is we do some sort of interpolation. We will keep our original grid and say that this blob will distribute its values to the surrounding grid point. Okay, so that's the interpolation part. And that's basically it. So you do a back tracing first and then you interpolate. Okay. There's 2 ways to do this. Okay, there's what we call let me mention the 2. So there's one called back tracing, which I'll explain in a second, and what we just talked about was forward tracing. Okay, so we have this grid node at Tn, and we know Un and xn, xn, yn. All right, all of these things are known to us, and then we can move forward to n plus 1. New position at tn plus 1, okay? And once we do that, then we interpolate. But we could also have gone back in time, right? We could have said that I am at my current time step where nothing is known, so need to solve for unknown by n at tn. Okay, and un is known. Known, xn is known, yn is known. What could we have done? So here we start at the grid point and go forward in time. We could also have started here and figured out where we came from, right? So this grid point was at some other point and it arrived from here, right? So this is where it came from. So that's the backtracing concept. I'm trying to figure out all my phi values at current step, and I look back where each grid point arrived from, and then I can interpolate from. Sorry, I thought I turned that off. Okay, so. Yeah, for backtracing, we figure out where our grid point came from, and then we can say, okay, this location at my previous time step had a particular phi n, which I can find out by interpolation. Does that make sense? Is it confusing? So with that, let's go back to the picture I had drawn. All right, so this is exactly what we were doing in this schematic here. We were going backward in time to figure out where we came from. So we came from here. Now, what is the phi of this blob then? To figure that out, we do the interpolation as both of you were saying from the surrounding grid points. And you don't need to just restrict yourself to this area. You can go to much larger areas. So I should go to as large an area as possible.
That would introduce many errors. Like we need to keep the grid size as fine as possible.
The grid size is the distance between these cell points, right? I'm saying to interpolate, to find out what this blob, what the phi of this blob is, I should use the surrounding 4 points. Or should I use the surrounding 4 by 4, 16 points?
The more the better.
The more the better.
Computation.
Exactly. So the interpolation will be more accurate if you use more points, but it also increases the computational cost substantially. Okay? All right, we can take a look right here. So, actually, okay, now. All right, so let's go and do a simple interpolation here. Okay, so let's use 4 surrounding cells for interpolation. What is one thing that you can think of to do if I give you this location and temperature at the surrounding nodes? The simplest thing that you can think of.
Weighted average, yeah.
Yeah, you can do some sort of averaging, right? The worst case, you would say, I will take T1, T2, T3, T4 and sum them, divide by 4. That is a terrible choice in this case because no matter where you are in the cell, you would always have the same answer. A more smarter thing would be to do some sort of nice interpolations. So I have 4 known values. What sort of interpolation can I do?
Weighted average with the distance being inversely proportional to the weight.
Right. So you're saying we do a weighted average with distance being inversely proportional to from the nodes. Okay? And what you have described is linear interpolation. Okay? The reason for that is so you can say, okay, this is my target xy. So first I will interpolate in x over here from there and there. Next, I'll interpolate in x over here from these two. Okay, and then the last thing we can do is interpolate at these new values that I now know. Okay, and that's a very simple and very effective technique. And you all know how to do interpolation? Okay. Okay. I guess I will tell you more in the next class how to do interpolation. Okay, so that's one possibility, and this is called tensor product interpolation. Now, somebody who said no, this will introduce errors, right? I'm making an approximation first here and then another approximation here. Why should I do that? I can form a paraboloid to the 4 known values. I can fit a paraboloid. Yeah, that's a valid argument. So here we could say that t at x comma y is basically a function of, not a paraboloid, sorry, a plane. We could fit a plane because we know 4 of these temperature values. You could say this is a, let me see, should I use A's? Yeah. No, I don't want to confuse you. Let me use alpha. Alpha naught plus beta naught x plus gamma naught y plus naught plus beta gamma and delta xy. Okay? And these are unknown coefficients. And if we know 4 values and we have 4 unknowns, we can do a solve, right? It's a very simple simultaneous equation solve. Another way to represent this would be, this is just a plus bx times c plus dy. So we have linear in x, linear in y, basically gives you the same equation. Okay? Alpha naught is a times c, blah, blah, blah. Okay, so this is a full surface interpolation, sort of. There's no smart shortcut that you first do it in x and then in y. By the way, is this the only way to do the interpolation here? Can you think of some other way?
Could you do the heat equation
The heat equation
based on the position of that cell in the center?
So, okay, you're saying based on this cell, we solve the heat equation.
Yeah. To each one of the nodes?
But wait, we're talking about just advection, pure advection, right? So we don't assume that any diffusion term at all. Okay. My question is, if you do this, if I say this is one way to do the interpolation, you first interpolate in x's and then interpolate in y. Your counter should be, why is this the only way? I have this other way. Why is that wrong? So what is this other way you could think of?
First y and then x.
Yeah, so I said I'll do first x and y. You should say, why not first y and x? And I'll say, yeah, fine. That's also a valid possibility. So Uh, let me just redraw this or so this is my square where I'm trying to interpolate. So you do first y using these two, and then in x using the new result. Make sense? So it either way is completely valid. The error you make will be slightly different, but the order of the error will not change. Okay. So yeah, somebody who likes mathematics says, no, I don't like this numerical trick of going using a tensor product. I will fit a nice plane using these known 4 points. This is my plane formula. The 4 unknown coefficients I can find easily by solving a 4x4 matrix. Okay, at that point, your counter should be fine. For this simple case, it works well. What if I decide that I want higher accuracy and I want a 4x4 surrounding stencil? How many coefficients do you have to solve for this now? 16 unknown coefficients to solve for. That's a 16 by 16 matrix already. Okay? And in 3 dimensions, how many? 64. So you have 4 of these planes, so you have 64 points. 64 unknown coefficients. That's a 64 by 64 matrix solve. So already you can see that's a 64-dimensional problem. It will take a few months to compute the whole thing if you decide to do that in 3 dimensions. Okay. So this nice technique of using cheap one-dimensional interpolations is very, very efficient computationally. It introduces a little bit of an error, but again, the order of the error is roughly the same as fitting a whole hypersurface. Okay, makes sense? So here, we do first interpolation in x, then with these interpolated values, interpolate in y, to get my phi at the right point. Everything makes sense? Anything is confusing? Okay, so we were discussing that the more points the better, and there are several smart schemes that try to minimize the number of points you have to use. So this is something I worked on in my PhD, and we basically came up with a very smart scheme that uses only these points, and that reduces cost. So it was, these are some of the things that you look at when you do hardcore numerical research. Okay? And if you think in terms of applications, now we can do a full-scale simulation in 2 days instead of 10 days. Okay? So those are the sorts of things you always think of when you deal with numerical methods. Okay, so now we have found out what our phi at this red point is using interpolation, some sort of suitable interpolation. What is the very last step? What do we do next?
Update the values in the surrounding grid points.
Okay, once more?
Update the values.
Yeah, exactly. So remember we said we started at this grid point, we figured out where it was in the past, and we know this blob value should not change in time. That's our d phi over dt equals 0. That's what it says. So once we figured out what this blob value is, we basically put it on our grid point. Okay, so we bring it back. And that's it. That's the semi-Lagrangian transport in full. There's again different flavors, different techniques, but that's the concept. Okay. And if we look at how well it performs to other schemes, this is a comparison of these two are Eulerian schemes, the two on top, fully Eulerian. And you can see they have huge errors. So that's mass going negative in the black regions. And here the shape is deformed. And if you use the semi-Lagrangian scheme and the modified semi-Lagrangian scheme, you don't see these errors to as great an extent. And the second test that I showed you yesterday, here it's more subtle, but if you stare closely, you will see that here in quick, everything is smeared out. You barely see any thin strands. If you go to the semi-Lagrangian and the mech, so this is a modified semi-Lagrangian, you will see that the thin strands are present. And without any diffusion term, these thin strands should be present. So this could be one of the tests that you might do for your project. Again, I have to think about it. Okay, so we know how semi-Lagrangian advection works. Any questions before we move on to the next topic? All right, so now we will talk a bit about, actually wait, one thing I want to mention is, here, what happens if CFL is equal to 1, exactly equal to 1? CFL, if you remember, is mu delta t over delta x.
It'll land on the node.
Yeah, that's what will happen. If CFL is exactly equal to 1, let's say we only have horizontal velocity. This node came from that node, and you don't need to do any interpolation. That node value is already known, right? So the interpolation errors will be non-existent, and your advection will be exact. Okay, but that's almost never the case. You never have CFL equal to 1, not just in one direction, but in all three directions, x, y, and z. If it is the case, then you don't need to solve the equation. It's basically constant velocity everywhere. So yeah, that's just one thing I wanted to mention. Okay, let me see. Is there anything else I want to mention? No. Okay, perfect. So now we can start talking about time integration. Okay, that slide I will show you in a second. Again, everything we have talked about is very simple, very elegant, but it's the basics of all numerical methods, no matter whether you do astronomy, solid mechanics, IO, physics, simulations. This stuff is what is used everywhere. Okay, so time integration. Now, let me give you one point. Let's call this y start, and if I give you the velocity of this point, u start, can you tell me where it will end up? At after delta t seconds. Is the question okay? Question makes sense? All right, so give me the simplest thing you can think of.
It would be y start plus u delta t.
All right, forward Euler, very simple. Perfect. Now, let me tell you that there is a y start with velocity u start, and there is a y end with velocity u end. This would basically represent a parabolic profile roughly. Okay? Do you see a problem with our approximation here?
FAU U is changing.
U is changing along the path in time. U is changing in time. So if we use this approximation, we will end up somewhere over, let's say, year. Okay, and that's a huge error in where I should be. Is that the only problem? Does mathematics care where you define y star to be? Can my y start have been here? Yeah, this could have been my y start, and I would have asked you what will happen in minus delta t time. The equations don't care, they will work exactly the same. So, how about going from y end to y start? If we use the same approximation that you mentioned, we would say ys plus, what would we say? Sorry. So you're trying to figure out what y start is, and it should be
Minus. Minus US start delta. UE delta T.
yeah, right? And okay, so these two should be equivalent, but they're not. Okay? Here, if we say this implies y start is y end minus delta t u start. Okay, and now we see we have two different approximations for the same thing. And the reason for that is u is not constant in time, it changes. Okay? So yeah, here you will end up somewhere over there. How do we fix this?
We can consider the higher order derivatives, even that would be a mathematical solution.
Okay, so your answer is we can use a higher order discretization instead of this first order discretization. This is just forward order. Yn plus 1 minus yn divided by delta t is derivative.
Yeah.
Okay, yeah. So you can use a higher order derivative. All right. Intuitively, if I give you these four things, y start, u start, yn, un, what is one thing you will try?
Decrease delta t.
Yeah, decrease delta t is the solution, but for a given delta t, right? I'm telling you, you're not allowed to change delta t. Give me the best solution you can with these four numbers.
Using average UE and US start.
Exactly. You know the u start and ue, you can do some sort of average here and get the midpoint velocity. Okay? So, to get a better approximation, we could use an averaged value or u. In example, we can use u equal u star plus un over 2. Okay, that's the midpoint formula. So this is called midpoint. All right, let's see. If we repeat our computation, what happens? So if we start at ys and try to go to yn, what will this be? Yn equal y star plus u delta t is equal to. Okay, so that's an approximation. You tell me, what happens if I know yn if I'm trying to go to y star? Let me fill out the right hand side.
YE minus
Right, so let me just write y start
is
to y end. And if I go from y end to y start, all right, so I will write, as you were saying, ye.
minus US plus UE over 2. Delta.
Okay, are the two approximations consistent? They're the same, right? Whether you start at S and go to E, or whether you start at E and go to S, C and D are consistent. So this is a very simple example of how we can start building up more accurate estimations of more accurate integration in time. Okay, and this is exactly what the Runge-Kutta methods use. I will spell it in a second. Can you finish writing? Everything we have used here is fully explicit. There are no unknown values, so I can solve for everything exactly. Okay. Okay, so what are Runge-Kutta methods? So the way you spell it is Runge-Kutta. Not Runge-Kutta, it's Runge-Kutta, all right? Okay, so these methods do something very similar. And if you look at RK2, that's Runge-Kutta's second order, this is the formula you will find everywhere. So it will say K1 equal F of Yn Tn, and K2 is F of Yn plus K1 delta T over 2, Tn delta T over 2, and finally Yn plus 1 is Yn plus K2 delta T. Okay? So, alright, but what does this mean? So this is the formula you will find everywhere, in every textbook, on every website, every video will show you this formula. Okay, so what this means is very, very simple. First, what should we do? Should we okay, so yeah, let's take an example. So a simple example of let's say a car is decelerating from 5 meters per second with acceleration minus 2 meters per second squared. Okay? And if we draw the path of this car, let's say at time equals 0, we start at y equals 0, 0, 0. 1, 2, 3, 4, 5, 6. Yeah. 1, 2, 3. Okay, so car decelerating from that, which means y equal ut plus half at squared, so 5t minus half times 2t squared, 5t minus t squared. All right, fine. So this is the parabola that should describe the motion of the car. And we are just using a very simple analytical example to see how things work. In reality, you will never have a nice equation like this given to you. Everything will be unknown. Okay, so let's say y say for time equal 1, 2, 3. Y is 5, 4, 5, 4, yeah, 4, 4, 4. Well, there's a 0, right? So 0 is 0, yes. And 1 is 1, 4, yeah, 4. For 2 is 5 to 10 minus 6, yeah, alright. And this is 15 minus 9 is also 6. Okay, and du by dt is 5 minus 2t. So we have here we have 3 meter per second. Here we have 1, 2, yeah, 4, 4, 3. Wait. Here we have 5 meter per second. We have 3 meter per second. And here we have 1 meter per second. Here we have minus 1 meter per second. Okay? So let's put down the points. We have 0, 0 here. We have 1, 4, 1, 4 here. We have 2, 6, 2, 6 here. 3, 6 here. Okay, so analytically the path of the car will look something like this. Minus 1 meter per second. Plus 1 meter per second. 3 meter per second. 5 meter per second. Okay. So if we do this this approximation that we were talking about earlier, let's say y start is 0, y end is 2, and we use our u is ue plus u start over 2, which is in this case 5 plus 1 over 2 equal 3, okay? And then we say if we know y start, y end. If we know y start, let's say this is unknown, okay? Y end is not known, that's what we're trying to find. We know y start, we can say is equal to y end plus u delta t, which is, sorry. Y end is y start plus u delta t, which is 0 plus 3 times 2, which is 6. Okay, so we have got the exact answer. Why? Why did we get the exact answer? Do you see what happened here? I'm sorry if I skipped a few steps. So I'm told that y start is this. I'm told that what u end and u start are given to me, so I can find the average. And then my question is, what is y end? Where will I end up? So I use my formula that we we thought of, where I will use the u average times delta t, and y start is 0, blah, 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 gives me 6, which is exactly the correct answer. Why is this exactly right? Why is there no error? Absolutely no error. Is this a coincidence or something we assumed? Yeah. The hint is look at the equation for y.
So if we integrate this and get the average using this equation, we will get the same average.
Oh, you're saying if we integrate this and integrate this. Why do you want to integrate this? If you integrate position, you get what?
No, I mean the derivative of this.
Okay, so derivative here, all right? So, yeah, that's exactly what you're saying is, y is a parabola, so derivative is a straight line, and if I have a straight line of u here, the midpoint will give me the exact answer, and for a parabola, this center derivative helps me jump exactly from starting point to end point. So it's just because our equation, starting equation was a parabola, that we managed to get the exact answer. This midpoint u will not be exact if this is anything higher than a parabola. If it's a cubic, fourth degree polynomial, the answer will not be exact. It will be close, but not exact. Okay? And I will let you do this on your own. You can check, well, why not? Let's see. So, if we use that un is yn is y start plus u start delta t, where will you end up? Delta t is 2 seconds. So,
5.
once more?
That's 5.
5,
5 times 2.
10. It says you will end up at 10 meters, okay? Which we know is not correct. I should be close to 6. So that's a huge error. Similarly, if I say I am given u n and I'm given y n and given u n, and if I go backward, what will happen? What is y n? Y n is 6. 6 minus 1 times 2, which is 4, right? So I don't end up at 0. I don't end up at the origin. I have a huge error. Okay? So, yeah, you can see that this first order approximation works steadily in this case. Okay, so what does Runge-Kutta do? We have not talked about Runge-Kutta here. We just said this is the formula. Okay? If you look closely at it, what it's saying is this is f, where f is del y by del t. Okay. This is basically saying, for my first step, compute what my derivative at the current time is. Okay. So if I start at the origin, that's my derivative at the origin, 5 meters per second. The second line, what the second line says is, okay, fine. From your starting point, yn, take a half step, delta t over 2, and use the velocity that you computed previously. So starting at yn, take my original derivative value and multiply by delta t over 2. That's like taking a half step. Okay. Once you take this half step, evaluate what the derivative, the f at this new position is. Okay, fine. And the final thing is, once you know this new approximation for the derivative, take a full step starting from your original position. That's it. That's the concept of Runge-Kutta. So you start with your original slope, take a half step. This gives you the new position. You evaluate your new slope at this half step. And lastly, you take a full step using this half step derivative. Okay, that's similar to what we did with the midpoint, right? We went to the midpoint, computed what the velocity was, and then took a full step starting from the origin. So that's the concept of Runge-Kutta. All right, so let's see how this works for the parabola example. You will see that this will not give us the exact answer. Okay. So what is? Let me say it is. So let's start at y equals 0, where u is given as 5 meter per second. Okay? So, what is k1? Del y by del t at 0 seconds. Which is? Sorry. Okay, I'll bring the table when we need it, but alright, what is k1?
5.
5. Alright, perfect. Now, so this is step 1. Okay, step 2 is take a half step. Okay, and my delta t that I want to go is 2 seconds. Okay, that's what that's what I'm interested in. What happens after 2 seconds? Take a half step, meaning where should we end up? So first, what is new y? Y at n plus half is equal to what? Let's look at the formula. So this is for K2. It's saying the new half y is defined as false, right? So let's write down this formula. This is yn plus k1 delta t over 2. All right. So let's fill it in quickly, which is yes.
0.
Once more.
0 plus
0 plus 5 times 2 over 2. Okay? So we end up at 5 meters. Yeah, that's my half step. Okay? So next step is then what is K2? K2 is defined as the derivative at half step. So this is defined as del y by del t at dn plus half. Okay, and which means, and I found out that this is how much I have moved, 5 meters. So what is the derivative at or at y equals 5 meters? What is the derivative of 5 meters? So what's the derivative? So the question is basically asking us, what is the velocity at this point? Right? And that we can figure out because we have the analytical expression. But again, in numerics, you never have these analytical expressions. So you do some sort of interpolation to find out what u is at that point. And then you take a full step. Let me see, I'm out of time, so I will continue this next time. Again, you see, we don't end up at this exact midpoint, which is at y equals 4. With the Runge-Kutta, we end up at y equals 5, which is close enough. Okay? In the earlier computation, we were just lucky that this is a parabolic program. So we will finish this the next time, and then I'll talk about what Runge-Kutta 4 is.